Signed in yet over here? I'd ask you to sign in before you go. And if you want professional development hours, make sure you provide your email address and write PDH beside your name. And we were supposed to have them here today, but the lady who was doing her PDHs had a family emergency and had to leave this morning. So we'll follow up. You'll get them by email. She's very good about that. Before we get started with the actual program, I'd like to introduce Rebecca Hildebrand. This session is co-sponsored by the Lehigh Valley PES chapter and the PES student chapter. And Rebecca is the chair of the student chapter. So, Rebecca? Sure, come on up.
Hi guys, I'm Rebecca Hildebrand. I'm the president of IEEE Power Energy Society for Lehigh University. We do all kinds of things like help sponsor these events, and we also just did a networking event with a couple people and a couple companies. And we love to have people interact from around the community as well as industry professionals in the power industry and our undergrads and our graduate students. So I'll hand it back over to Al.
Thanks, Becca. How many people here are students here at Lehigh or elsewhere? How many are not members of the PES student chapter? Okay, if you'd like to join, please see Becca afterwards, and she'll be happy to take your name and put you on her mailing list. If you have interest in this area, my one and only sales pitch is it's the best way to network with the best and brightest minds in the power industry. You'll never find better resources. Throughout my career, when I had a problem, I always had a technical guru I could email and say, hey, have you ever learned into this, and what did you do? It's a great resource to have under your belt. Before we get started with this program, a couple upcoming programs. On April 19th and 20th, we're going to have a speaker, another distinguished lecturer from the Power and Energy Society here. He'll be here on April 20th, and he'll be talking about electricity access in developing countries. And the night before at PPL, but I got to say it's not downtown at the normal auditorium. It's at the PPL Training Center, which is at just off of Route 309 and Walbert Avenue. The announcements that's going to be coming out in a week or so will have directions on how to get there. But his focus will be a little bit different here. It'll be the role of microgrids in energy poverty alleviation. And Henry has a good talk on that because he just recently completed a year as a Fulbright scholar in Zambia, Africa. And he said the brownouts were almost dead. So he has firsthand experience with how it affects your life. And the final advertisement for the upcoming event on May 2nd, Jim Daly. Jim, if you raise your hand. Jim is going to be giving a talk at the Walbert Training Center also, on the 1547 standard, IEEE 1547, which covers a lot of information on how to integrate generation with the power grid. And Jim was part of the group that wrote that standard. It's been given around the world, and we said, we have a guy here that can give it locally. We won't have to bring a distinguished lecturer in for that. We have him. So Jim will be giving that on May 2nd out at that same Walbert Training Center. This talk, the talk that's John given, yeah, Jim, go ahead.
It'll be repeated here in the fall.
Okay. I didn't know if that had been confirmed or not. I know we talked about it.
Yeah, I just spoke with Rudy about it.
Good.
Rudy about it will be repeated here in the fall.
That's great. Terrific. Like I said, this was done last night at PPL. We had about 50 people there. I think the version tonight, we got about a half hour left for John to talk tonight, so it's going to be a little bit abbreviated, might have a little bit different focus, especially for the student population. I'm not going to tell a lot about John. His bio is out there. The abstract for the talk was out there. Hopefully you've read that. John's been at GE for about 10 years or so. He's got about 40 years or so in the power industry, a lot of different companies. I think he said 12 years was the most he's been with any company, but I'll let him cover any details he wants to. He was a friend a long time before the 10 years at GE, I first met John when we were on the PES governing board together. I was the treasurer, John was president, 2006 and 2007, and I later became president in 2010 and 11. He's also a distinguished lecturer for PES, travels around the world giving talks on this and many other subjects. He's well versed in a lot of areas, but without stealing any more of the time, I give you John McDonald.
Thank you.
You're welcome, John.
So as Al said, this was a topic I went through last night, but I've added some stuff at the end for students. And Al talked about the student being a student member. The IEEE student members receive a publication called IEEE Potentials. It's a magazine for students. And in 2011, I wrote an article about my experiences, my very first full-time job, my very first full-time engineering job after I got a bachelor's and master's in AA at Purdue University. And so I spent 5 years with Bechtel Corporation in San Francisco. And I wrote an article about what did I learn in my first full-time job, what were the lessons I learned. So we'll finish with that, okay? And like I did last night, let me say that I may refer to some different articles and work that I've done over the years. And if you'd like copies of that, make a list, okay, of those things you're interested in, and send me an email. Whatever you're interested in, I'll send it to you. For instance, at the end, this article from IEEE Potentials, I have a PDF of the entire article. So I'm going to summarize, some things, but if you want to see the whole article, just send me an email. I'll send you the article. Okay? In addition, I can't tell you, like Al, how important IEEE PS is. This is my 46th consecutive year of active participation in IEEE and IEEE PS. 46 years. And, three things that are important as I think back. One is I have a much better appreciation of technology from a global point of view because of all the stuff I've done with PES and get different perspectives and travel around the world giving talks and courses. 30 years of leading standards work, so real good perspective on technology. Second is there's a lot of leadership positions. It's a volunteer organization. And if you volunteer to lead in a volunteer organization, everyone will say, sure, we'd be happy to have you, right? And you have limitless opportunities for leadership, right? And the more experience you get in leadership positions, the better off you are. And the more you put into something, the more you get back, right? So if you just go and attend the meetings and go home, yeah, you'll learn some things, but if you're a leader, you'll get much more out of it, okay? Third thing is the network of industry contacts that you build through IEEE and IEEE PS. And all the different jobs I've had in my 43-year career now, working full-time in this field, have all been through industry contacts. I wouldn't be at GE today if it wasn't for a friend of mine in the industry who called me at home and said, there's an executive position opened up at GE reporting to the CEO that's perfect for you. And I was very happy doing what I was doing, international consulting for 12 years. And he said, I can line up an interview for you with the CEO in 2 days if you're interested. And I said, yeah, why not? And so I didn't know about that opportunity if it wasn't for my friend. Okay? So you want to do what you can to expand your contacts. And one of the most important things for students is LinkedIn. You want to build your profile on LinkedIn and keep that up to date and as detailed as you can. What I suggest is we can get connected on LinkedIn. I want you to look at the profile that I have. I've got about 7,500 connections on LinkedIn from all over the world. A lot of people I do keep in touch with on a regular basis. Industry people from all over the world. Okay. So those are some. We'll talk about that at the end also. So I've written a lot of articles. I've co-authored 4 books. And if you're interested in some of the information on the books, I can send it to you. There's one called Electric Power Substations Engineering. It's in its 3rd edition. It's 22 chapters on all aspects of substations. I wrote the chapter on automation of substations, but there's 21 other chapters: cybersecurity, asset management, energy storage, physical security, HVDC, bus structures and the trade-offs between different bus structures. That book is one book in a 5-book set called the Electric Power Engineering Handbook. So if I was a student today and I wanted to invest in one reference, I would get the 5-book set called the Electric Power Engineering Handbook, and that covers everything in the power engineering field, those 5 books. The substations book is one of those 5 books. Okay. The second one is a book on smart grid that we're just now updating for the 2nd edition. I wrote chapter 6, the last chapter of the book, the future of smart grid. But that's a really good book. Covers, it's like 500 pages of technology, standards, policy, international differences on smart grid. Third book, I've been working in the SCADA field, supervisory control and data acquisition, for almost all of 40-some years. And a woman professor from India, and I spent a couple of years, Minnie Thomas, and we wrote a new book called Power Systems SCADA and Smart Grids. 335 pages on SCADA. And that just came out a year ago. And if you're in, that was reviewed a year ago in the IEEE Power Energy magazine, the January-February issue of last year, by an executive at Dominion Virginia Power, by Dave Root, wrote the review. Okay? And I've got information on the books if you're interested in any of the books. Okay? So again, I'm going to refer to things, make a list, okay? Send me an email, and tonight I'm going to talk more of a university, more of a student approach to the material, and then new material at the end from what we did last night, and have less time, so we'll go through it a little bit faster. Okay, so the things we're going to talk about is, as a student, one thing to keep in mind is, and we'll talk about this at the end, is try to get involved in as many things outside the university as you can that are career related. Working, internships with different companies, right? The IEEE group, right? As a student, write a paper, so you can go to a conference and present the paper. Okay? At PES, we have a lot of money each year to help fund students to travel to conferences.
About, I believe it's 150,000 a year.
So that, to help bring students to conferences. There's no better experience, as a student, to come to a PES general meeting, for a week, which will be in Chicago this July. But you need to know what's happening in the world around you as a student. Okay? We do an industry, but you want to as students. So we'll talk about some trends. As a student, you want to think about the solution. You want to, at Georgia Tech, we teach students to think of the big picture, and they have a special program called systems engineering. The whole system, not just the component. So I want to show you examples of solutions for smart grid. Okay, not just the component, but the big picture. What do we mean by big picture? As a student, you want to keep up with industry standards. Jim's going to talk about 1547. It's a very key standard on integration of renewables into the grid. But that's one of 16 foundational standards for smart grid. Okay, we're going to talk about tonight. Industry standards and the importance of industry standards. And then a real hot topic today is microgrids and distributed generation. And we'll spend a lot of time, both in general and work we did in the IEEE PES for the Department of Energy in the United States. Okay. And anytime, as we did last night, anytime you have any questions or comments, stop me. Don't wait till the end, but stop me and we can talk about it. Okay. So let's look at the trends. So as I said, as a student, you want to think of the big picture. A lot of times we're working with a microprocessor-based device here, like a relay, and so what happens is we get we look at the relay, we look at the capabilities of the relay, the functionality, but we have to remember that that relay has two-way communications and it can be part of a bigger network, right? And from a business point of view, if I'm the customer, I get value from the box, the relay, but I get greater value when that relay is part of a solution. An example would be a substation automation system in a substation, or part of a remedial action scheme, right? Looks for trigger points and disturbances on the grid, tries to isolate the disturbance, prevent it from cascading, right? Or the relay is part of a fault detection, isolation, restoration solution, okay? Not just the box itself. And systems where we have a lot of systems in the grid that are more products, like energy management system is the standard control system or SCADA system to manage generation and transmission. The distribution management system for distribution. Geographic information system, right, keep track of the assets and the digitized maps of the service area. And the outage management system keeps track of the network model and which customers are connected to which parts of the system and who's out, okay? So those are more products. The solution, what we do is we spend time with the customer, and you can't ask enough questions of the customer and really find out what the needs of the customer are. And then, once we get that information, we say, what technology components can we put together into a solution to address the needs of the customer? So it's driven by the customer. Success is really not just technology, but we need to look at industry standards and policy. Okay? So as a student, you know, technology is something we love. And we could stop there and just study the technology and be happy. But we need to think about standards, because today when we have technology components from different vendors, they need to talk to each other. You know, the different vendors. And the only way they can do that, we have to comply with the same set of standards, right, to be able to be successful. And then policy is what incentivizes the customer to buy our technology, to buy our solution. So we try to influence policy. If you just focus on technology, you could have fantastic technology, but nobody buys it because the policy doesn't incentivize the customer to buy it. Okay, so we need to work on all three. And I would say there's a fourth one that's overarching, particularly important for students, and that's what's the business side of the technology. Okay? Because you could graduate, work for a company, have a great idea for a technical project, but your manager or the executive in your organization says, okay, you have this technical project, but I'm not interested in the technology. I want you to tell me what the costs will be to do it. Tell me what the benefits are that I'll receive. Right? So you have to be able to anticipate, calculate from a business case. But more importantly, tell me how many years will it be before the benefits curve crosses the cost curve. What's the payback period? Okay. So if the benefit-cost ratio might be 5 to 1, or there's 5 times the benefits and the cost, which is very good, the payback period may be 12 years to 15 years. What's the financial aspects? And the reason I say that is in 1997, a market researcher surveyed over 100 utilities in the US and Canada at the time and said, what's the leading obstacle in implementing substation automation in your utility? The technology's there, it's field proven. How come you haven't implemented it to a greater extent? And the number one reason was difficulty putting an economic justification together, business case, for engineers, 1997. So it's a good wake-up call for us. You know, if we only teach technology, we're not doing our job. You know, we have students go out, start working, fantastic ideas for projects, but many of them may never get approved. They never get to do it. It's very frustrating because we aren't trained on how we think from a business point of view. So I wrote an article in IEEE Electrification magazine recently. There was microgrids, but it was the business side of microgrids, not the technology side. Okay? I said, let's cut through the hype, the technology hype, and look at microgrids from a business point of view. Okay, it's in IEEE electrification. So next is self-healing. And so, you know, as a student, we think of logic, and then we want to test the logic, so we install it in the field. And once it's field proven and the recommendations are sound, we can close the loop on the logic, right? Take the human out of the loop. And that gives us more of a capability to self-heal, right? For the group to self-heal. Take the human out of the loop, okay? And one of the goals, particularly of distribution, with fault detection, isolation, restoration, is to be able to detect the fault quickly, locate it, isolate it, then restore service upstream and downstream of a faulted cycle. Okay? And if we can do that without a human in the loop, we can get it done in a minute or two. Okay? And then next is resiliency. Resiliency, which, you know, particularly with weather, you know, we've had a lot of extreme weather events in the U.S. which have created outages, and so there's more concern about the grid resiliency from customers. And one of the things we did at GE, because we wanted to test this a couple of years ago, is we used Gallup, a professional polling organization, and we surveyed thousands of utility customers all over the U.S. And one question we asked was, you know, how would you be willing to spend $10 or more extra per month on your electric bill? Pay $10 or more extra if all that extra money went to making the grid more resilient. You know, and I think it really surprises us that 41% east of the Mississippi said that they would, and 34% west. Okay? And you know, the ones east of the Mississippi have had 3 times the outages than the ones west, so that's why they're more willing to pay. But 41% is a lot, which means that, you know, just in that survey, it shows the resiliency of the grid is so much of a concern, and outages and duration of outage, frequency of outages and duration, that people would pay more if that money went to making the grid more resilient. And then at the university, you might get into things like data, you know, managing data. And there's techniques, particularly today with the impact of the Internet of Things, okay, which is increased connectivity. So the Internet of Things, the Industrial Internet Consortium was formed a couple of years ago, and GE, AT&T, IBM, Cisco were founding members. And we're looking at, it's called the next productivity revolution. How can we leverage 3 things: connecting machines, intelligent machines, with analytics, right? Software and analytics, and people, no matter where the people are, connect any way you can, any time of the day. Connect those together and you'll have more information available, more readily available. And how can we leverage that, you know, to be more productive? And so at GE, just within the last year, our CEO formed a new business called GE Digital, right? And that has a function inside GE. So every business within GE has a GE Digital component, which is looking internally at how can we leverage this to make our own businesses more productive. And then the external component as a business is the products that we sell, the technology we sell. How can that take advantage of it, right, to be more cost effective and have more functionality? We're using more of the cloud today. The Predix platform, which you've seen in the news. Many companies now are writing their own applications on GE's Predix platform. Microsoft just signed an agreement with GE. A good part of that platform is cloud-based. Okay? And the future EMS, which is the generation control SCADA system for utilities, will be totally cloud-based in the future EMS very shortly. All the 4 big EMS vendors are working on the new platform. So we need to think about big data, the cloud, and social media. You know, utilities are now empowering their customers with social media. So instead of a landline phone, if you have one, pick it up and call the utility when there's something to report. you send a tweet, right, to the utility with the outage information or whatever you want to communicate, and we can actually parse the tweet and put that directly into the outage management system. And we can associate the fact that you sent the tweet by taking your Twitter handle and putting it in your customer record and the customer information system at the utility. So that's what's happening. And the reason is, in the same survey we did a couple years ago, we asked people, what's your preferred way of interacting with your utility? And 70% said they prefer to interact through social media, not through the telephone or any other way. Okay. So how can we do that? And then lastly is convergence of IT, so that's the information technology side of the utility and the operations side. And the bottom line for this is, typically, we'll have devices and systems on the OT side that have a lot of valuable information, not just for the operators and the controller, but for projects I've done the last 15 years, I've identified 25 to 30 business groups in the utility, like maintenance, power quality, asset management, that could provide more value to the utility with information that's on the operations side, in devices, in systems, that many times these business groups don't even know exists in the field. Okay. An example would be the protection group buys a relay. Okay. We operate very siloed. So the protection group buys a relay, puts it in the field, connects it to a circuit breaker, and their focus is on protecting the power system. But in that relay is the I2T information on the circuit breaker. When there's a fault, right? Contacts open up to extinguish the arc. What's the magnitude of the current? How much time does it take, right, for the arc to extinguish? Well, the manufacturer of the breaker says when that breaker's experienced so much I2T, it needs to be maintained. And once the operations counter, how many times is it operated? That information's in a relay. But I can't tell you how many utilities where that information is in the relay, not extracted and not being sent over to the maintenance group. Because the relay group doesn't care about that information. They bought the relay, they want to protect the power system. There's no incentive to do sharing across groups, to break down the silos, and share it. So that's why holistic is so important here. We need to think organization-wide with what we do. Okay? So everything that you do, think of the big picture of students, not just a group, not just a component. All right? So we've been adding intelligence to grid for a long, long time. So what we're talking about more recently is a smarter grid, not just a smart grid. And what's in light gray is what we've been doing at each of the 3 levels, and what's in light green are the new things that we're doing. So again, for instance, voltage control. If I control voltage, I directly control load. Right? Voltage is directly proportional to load. So the way we can manage load is we can raise and lower the voltage. When I control reactive power, I can control losses. I can reduce losses. And there's a very strong business case today with voltage and reactive power. We're integrating those together today to do integrated volt-var control. That's why it's shaded halfway. Left side, we've been doing voltage control by itself for decades, doing reactive power control by itself for decades, but now we're integrating them together. That business case, for every dollar I spend in that application, I typically get about $5 to $6 back. The benefit cost ratio is very, very strong. Payback period is short. Okay? We'll talk about renewables. We're adding more sensors out in the grid. We have a lot of areas of the distribution system today that we don't have any information coming back. These 2 boxes here, distribution management, distribution automation, that's the focus today. Distribution management system at the control center, managing the increased complexity of distribution because of renewable. And downstream of the substation, distribution automation on feeders, distribution feeders. And we'll talk about smart metering. The meters give us a lot more information for DMS, for distribution optimization, than just to generate bills. Okay. So after talking to a number of utilities and getting their needs, business needs and operational needs, about 9 years ago, we took that information and we said, how can we put technology components together to make integrated solutions that address as many needs as possible, with electric utilities. And these are the 6 solutions. So it's asset optimization, where we're focused now on transformers, okay? Because we have an aging infrastructure, and transformers today in the U.S., the average age is about 42 years of a transformer. So how could we, for a multi-million-dollar asset, how can we spend a lot less money and know the health of that asset on a continuous basis? Okay. And then demand optimization. So we're looking at demand response, right? Taking customer loads and aggregating those up and using those as a dispatch tool. Smart metering and communications, optimizing the distribution system, optimizing transmission, right, with synchrophasers, using synchrophaser information, remedial action schemes, the EMS of the future, which is the control system of the future for generation transmission. A lot going on there. And then workforce and engineering design optimization. Okay. So last night we talked about this, where in our energy industry in the United States, PricewaterhouseCoopers issued a report recently that said 40% of the employees today in the U.S. in energy and 60% of the executives will retire within 5 years. Okay. So, as young professionals, there's great opportunities in the power and energy area because of so many retirements. Okay. So the demand continues to be great, but the supply of qualified graduates hasn't increased to meet the demand. Okay? And I'll give you an example, and this was almost 10 years ago. When my son went to Georgia Tech, studied electrical engineering, specialized in power, had 4 different internships as a graduate, and took a couple power courses from well-known professors. And he had 2 companies, GE and Commonwealth Edison in Chicago, bidding on him when he was interviewing because he had a lot of work experience, really good academic experience in power. And so ComEd and GE were bidding on him with a signing bonus to try to get him to say, yes, I would work for you. And when he accepted the offer from GE, he received, this was 10 years ago, $9,000 signing bonus just to say I will work for you. And that was 10 years ago. The demand, if it's even greater today, the supply is not much different. So if you make the right choices, the courses, and get as much work experience as you can, you'll be in demand. Because so many companies, we hire electrical engineers, but they haven't specialized in anything, and then we have to take distance learning courses while they start work, like at a utility or a vendor like GE, and they have to learn power, right? And they're not as productive in the beginning of their career because they didn't come out of school, right, with the work experience and the courses in the power field. So it means a lot to a company where you have more qualifications at the time of graduation. So workforce is very important. Okay? So these are the solutions, and this is the technology roadmap, color-coded by solution. And say, okay, what are the technology components that we need to put together from different vendors for that solution? So this is the office and control center, the substation, downstream of the substation, on the feeders, on the utility-owned, which could be anywhere in the service area, the customer's premises, and the orange up there is the field crews in their trucks. Okay? So we can just take a look at the blue boxes, because that's what's most important today, the distribution of the strongest business case. And up here in the office, we have software applications in blue, 4 boxes up on top. And we have the DMS and the OMS systems. Okay, that's our systems and software, that's the logic. But we've begun to distribute the intelligence now. So instead of just using a centralized architecture where all the logic is upstream in the control center, we've distributed intelligence to the substation level. So here's applications running at the substation level. Okay? And we have other microprocessor-based devices in the substation. This is the station controller, or the data concentrator, kind of like the master station for the substation. Here we have switches and breakers, sectionalizing devices. We need these to support the logic up above for fault detection, isolation, restoration. If we want to isolate the fault, open up switches on either side. Right? That's the logic. This is the actual equipment out on the feeder. And here we have capacitor banks, voltage regulators to support the logic of integrated volt-var control. Which, again, this logic could be up here, or it could be at the substation level. Either one. Right? So, what you want to, this is what I mean by think of the big picture. Don't just think about a relay in the substation. But that relay is part of a larger scheme here. And that larger scheme provides much more value to the utility, right? The integrated solution. So the keys with a solution is integration of different technology components. And when we comply with the same standards, we have successful interoperability. We can talk to each other and we can exchange information with each other. Okay? So when we talk about integration,
John, I'm sorry, on that
Yeah.
last slide, you had distributed energy resource manager.
right?
And I guess I'm wondering, what does that kind of package do, and does it apply in all regulatory models, or more so some than others?
It really, I would say it applies in all. And what we're trying to do there is all the distributed energy resources around the grid is because they're difficult to forecast, we can't base load them, is to manage them to the greatest extent possible. So that's a function. And how do we manage all the distributed resources around the grid? And it could be done a couple ways. One would be, instead of a separate box here, it could be integrated into the DMS. You know, so these blue boxes, each of the applications have what we're adding is functionality. Each of those blue boxes to be able to, you know, not just estimate the load. You know, we have applications up here like 3-phase load flow, optimal feeder reconfiguration. Each of those now include the impact of distributed generation. And so the DMS, each of the applications now includes the ability to incorporate the impact of distributed generation. So what we really want to show there is, by having a separate box up there in green, is to show that functionally we need to take that into account. How we actually incorporate it could be, doesn't necessarily need to be a separate system or separate application, but it needs to be somewhere. Okay. It's a good question. It's not trivial. When you have a fault and you restore the system downstream, your loads are changing because you have distributed generation that's intermittent in your loads, and you put them together. Your load could be real low, and then the sun goes behind the clouds, and all of a sudden the load jumps up instantaneously. So you have to, how do you account for that? Okay. So one thing with meters is we can take the voltage from certain smart meters. We can ping those through the network and bring that information into the network model, the DMS. So when we do volt-var control, we want to flatten the voltage profile and lower it. But we have a standard in the United States that says the voltage at the customer's premise must be 120 plus or minus 5%. They need to be within, right, 126, 114 volts. We don't want to get too close to 114. Okay? So if we have a real long feeder with a lot of voltage drop, then we may have a problem when we do volt-bar control. Okay? So we need to monitor that. We can use smart meters for that. Also, each smart meter has the ability for last gasp communication. So you have an outage, and even though there's no electricity, there's enough energy in the capacitor in the meter for one last communication to the utility that says, hey, I have an outage and this is the time it occurred. The geographic information system here is the reference system for the network model, for the DMS, and the outage management system, the OMS. Very important that that's kept up to date. We take the DMS, anytime like a feeder breaker trips or there's a status change, we know within 2 seconds. And we send that information to the OMS, the outage management system, because the outage management says, okay, this feeder's de-energized. Through the network model, I know all the customers connected to that feeder. And now that that feeder's de-energized, I know all those customers have an outage. Okay? The time it occurred. And then what we've traditionally been doing is using landline phone calls from customers and the caller ID system, right, to relate the phone call to the customer record to bring it up for the trouble call operator. And a lot of the young folks, right, don't have landline phones because we don't need them with a smartphone. So how can we use social media to a greater extent? Article I wrote over 3 years ago. I can send you a copy of it if you're interested. And the article was titled, "How can we use social media to accelerate the restoration of electricity after an outage?" It was a cover story in Power Grid International magazine about 3.5 years ago. Okay. So let's look at standards. And these are the 16 foundational standards for smart grid. One of these is IEEE 1547 that Jim will talk about. You know, the main thing with smart grid is, think of where does smart grid start and where does it end? Okay? The G, we say smart grid goes from turbine to toaster. Turbine to toaster. Generation, transmission, distribution, and the end-use customer. It's a pretty wide landscape. And so that's why the smart grid book that we did, is about this thick, because chapter 3 is all about all the technologies that are involved in smart grid. So that's a pretty wide landscape. So it takes a lot of words, right, to cover all that. But also, what are the standards most important? Whether it's generation, transmission, distribution to the end-use customer. And again, we went through over 100 IEEE standards to touch on smart grid. We went over 100 IEC standards, plus other standards development organizations. And these are the 16 most important. So, as a student, if you're doing research in smart grid, you should have at least one or a couple of these standards involved. If you're at a utility doing a project or writing a procurement spec, you definitely want to have these things involved. And as a vendor, if I'm developing a product, the G, I want to make sure I know what standards I need to incorporate, right, in the development, the design of a product. Okay. And again, what's nice today around the world is if we look at 3 different levels of the grid in the architecture. So at the top level, we're control center to control center. So you're at PPL, and you want to communicate information to PJM, okay? Or you're at PPL, and your EMS for generation transmission is to communicate information to your DMS. So you have a DMS for distribution, EMS for generation transmission. The worldwide standard today for that control center to control center communications is, we call it ICCP, Inter-Control Center Communications Protocol, or IEC 870-6. Okay? So whenever, if you're a SCADA vendor, there's 4 key EMS SCADA vendors do the EMS type of work, generation and transmission. And every system that they develop anywhere in the world, it has at least one ICCP port, probably multiple ports. Okay? So that's top level. Then we go down control center to field equipment. Primarily two protocols that are used worldwide. For North American suppliers, DNP3, widely used in North America, Distributed Network Protocol 3, which a couple years ago we took through the IEEE standards process, so it's IEEE 1815, widely used. And again, there's a DNP user group website. There's a lot of very good information about the protocol. Also, about what companies, independent companies, the user group is approved to do independent testing of vendors' products. We talked about this last night. If you're in a utility and you're going out for bid for a substation data concentrator, you can say in your requirement, in your procurement spec, I want to make sure in your proposal include a certificate that what you're proposing to me, the equipment, has been tested by one of these independent companies, and that the DNP protocol has been accurately implemented in your product per the standard. And it was independently tested, and this company that did the testing was approved by the user group of the protocol. The same is true for, well, we'll get to that, but the same is true for IEC 61850 in the substation. That's called the UCA International User Group. And again, the same thing occurs, okay? So DNP3 in North America, if it's a European supplier, they don't use DNP3 and they aren't that familiar with it, which is kind of a red flag in North America, like ABB, Siemens, Schneider. What they're more used to is IEC 870-5, 101 for serial communications, and 104 for network communications, because that's the predominant SCADA protocol outside North America, in Europe. And then if we're in the substation in the field, we'll see DNP3 or IEC 61850, which is truly the worldwide standard in substation automation, communications, and architecture. Okay. So what's nice is we converge to a very small number of choices. So it's much easier today to determine, what you should use. Okay, much easier than before. So if we look at microgrids or just distributed generation, here we have generation. Here we have the switch yard outside the power plant. So one of the most critical transformers, right, on the grid are these generator step-up transformers just outside the power plant. So these typically will have some amount of transformer monitoring and diagnostics on them. Okay, to look at the health. Because if you lose one of those, that's your coupling of the generation right to the transmission system. So part of your power plant won't be able to be used, right? Some of your output. So generator step-up, a GSU, usually has more. We have different levels of transformer monitoring that we can provide, from a simple unit which looks at pressures, temperatures, and maybe one or two gases dissolved in the oil, to the ultimate, which would be a unit that can detect up to 9 different gases dissolved in the oil in the main tank of the transformer. So you find more investment in the transformer M&D devices on the generator step-ups. And I've got an article I did about 15 years ago, that, again, I could send. It was an Omaha Public Power District, a generator step-up transformer, a Westinghouse shell-form transformer design. It was known to have static electrification problems. And when this started failing, we couldn't de-energize it because it was right outside, too critical. But we used partial discharge acoustic monitors on the outside of the tank of the transformer in strategic places, and we could listen to the signature of the static electrification, and we could control that based on the temperature of cooling liquid through the transformer. And we extended the life of this transformer that was failing by over a year. Okay? And OPPD put a spec together, went out for bid, got proposals in, ordered a contract. The transformer was built, tested, brought on site. A outage was scheduled, and then it was replaced. So we never had to de-energize it. We strategically used partial discharge acoustic sensors and microprocessor-based and monitoring diagnostic equipment at the transformer to keep track of it. Okay. So then we go down to transmission, and we can, the renewables, the DG at the transmission level would be large scale, right? Wind farm, large wind farms, concentrated solar, the mirrors, right, that reflect the sun up to a boiler, like in see in Arizona and New Mexico, or large fields of PV panel. We get the distribution. You can see fields of PV panels, maybe some smaller wind farms. Then we get to the end-use customer, and we'll see maybe PV panels on the rooftops of homes, right? But the thing we take into account is that the distribution system was designed for what? Electricity flowing in one direction, from source to load. Typically it's radial in architecture, so the feeder comes from the substation down to the last customer and stops. There's no tie point to another feeder in the substation. And the protection settings were done based on short circuit studies that looked at the source side contribution to the fault only, right? There was no load side contribution. Okay. But power flowing in one direction. We put distributed generators on the feeder. Now we have load side contribution if there's a fault. Okay. We also have open circuit over voltage possible due to unintentional islanding. The fault currents, when a fault occurs, the fault currents that we get, our short circuit study, we looked at source side contribution only. Now we have a load side contribution. So the protection ratings may not be the right settings based on the fault currents. And the other thing is the fault currents from the load side contribution due to the DG are varying because of the intermittency of the DG. They're not constant. And because of the volatility of the intermittency that is created on a distribution feeder, voltage regulators there's a lot of stress on the regulation equipment. Okay? So, so you have to think about that. What are the operational impacts of distributed generation? So one of the things that has grown in popularity recently is microgrids. And it's true. Originally, when we talked about microgrids, more of a niche technology for university campuses, right? Military bases, and rural villages.
Hospitals, maybe?
Huh?
Hospitals?
Yeah, in a sense, hospitals though have, they've done a good job of having their own backup generation because for critical care and all that stuff. So hospitals are pretty self-sufficient already in their design. Where a lot of times, and they don't have as much of an emphasis on renewable generation as, say, a military base. The federal government in the U.S. has stressed on military bases, we want to use as much renewable generation as possible. So then you get into a situation of a large military base. You've got these renewables now, they're intermittent. You've got this load that's constant. How do I manage all this, right? Or a university campus, which there's pressure to have more renewables on the university campus. But again, if you look at originally the electricity distribution network of a university campus, it's been modified and added to in piecemeal fashion over many, many, many years. And you look at it and say, oh my God, there's so much we can do here to optimize this, right? Over many, many years, things have been added, and there's overlaps, and there's things that are duplicated, and so you put renewables on top of that. And it's a complicated situation, you know, so we're taking a fresh look at university campuses and say, how can we optimize this campus? Okay. And then rural villages, these rural villages are saying, I don't have a tie to the grid, but if I can harness Mother Nature, you know, to help fuel cells, the sun, wind, whatever, maybe that can help supply generation, and I can use less of diesel generators, right? And that's what happened here with in British Columbia. This was the first GE project, Microgrid project, at Bella Coola in British Columbia, because they did have fuel cells, solar generation, some PV panels, low-head hydro, your traditional diesel generation, which you can base load and you can ramp up and down and regulate the system. But there's industrial and residential load that needs to be satisfied on a continuous basis. So, you know, how can we meet the load requirements but maximize the use of fuel cells, solar, hydro, right? And minimize the use of diesel, right? Because the cost of getting the diesel fuel to a rural area is very expensive. And then whenever the diesel operates, it emits CO2 to the atmosphere, right? So let's say, how can we minimize this and maximize on a continuous basis? So that's what the microgrid controller up on the left has logic, right? On a continuous basis, it's optimizing the microgrid. Okay. And then a good example, if you want to take a tour, not too far from here, and see a couple microgrid projects. There's 3 microgrids that have been put into the Philadelphia Navy Yard, not too far from downtown Philadelphia. And it's a project that Alston Grid started on years ago. And then a year and a half ago when GE and Alston Grid combined forces, you know, it's now, instead of Alston Grid, it's now GE. So there's 3 microgrids here. It's an effort here to take an old Navy Yard and do industrial development of that area. You know, bring businesses in, commercial buildings, a lot of new development, and use microgrids and renewables to help power what's there. Okay. So at GE, we've established a microgrid center of excellence at the Navy Yard, which you can tour that center of excellence room. We put in a DMS, distribution management system, and a control center with a video projection screen, map board. You tour that. There's a network operations center, and then the 3 microgrid projects. Okay. And working with Department of Energy has funded some of this. PIDC is the Industrial Development Corporation, where we work with PJM, Burns and McDonald, Penn State University has been very actively involved, and Pico Energy is the local utility. So again, we put a DMS SCADA in. We're using, this is open source software for one of DOE labs. The PNNL is the Pacific Northwest National Lab. And they have what's called Grid Lab D, which models the power system on a 3-phase basis. And you can use it to run load flows on a 3-phase unbalanced basis. Open source software, free, anyone can use it. There's a supervisory microgrid control system, and then we have microgrid automation control systems at each microgrid. So, you know, with the intermittency of renewables, the load is there, but if the sun goes, between the clouds or the wind dies down, you still have to satisfy the load. Right? So how do we bridge that? And you know, we could use energy storage. We could use fast start thermal generation. When we look at energy storage, we have to think, what's the application? Is it an instantaneous application, which is more power related? Or is it longer term, more energy related? Because there's different energy storage technologies. Lithium ion is better for something that's needed faster, instantaneous. Or maybe a sodium sulfide is used for more peak deferral for a longer period of time. So we look at the time frame. You can't, one chemistry is not best for all time frames. Okay, you have to look at different time frames. Now, as we add more and more renewables, particularly on the low voltage network, like customer distributing the lower end of the distribution system, at the edge of the grid, we get in the situation where as the penetration of renewables at the edge of the grid grows, we're putting a lot of volatility on the distribution system. And so one example that I wrote about on the next slide is at San Diego Gas and Electric, where they have one feeder that had over 35% of the homes on one feeder all have rooftop solar panels. 35% of all the homes on one distribution feeder. These homes are along the Pacific Ocean, very nice homes, nice subdivisions. But you know, in the ocean, you have fog in the morning, called a marine layer of fog. And as that fog burns off, all these 35% of the homes on one feeder go from 0% to 100% instantaneously. So they all begin generating at the same time. Imagine the voltage on that feeder spikes and then oscillates, right? So what's in the substation? In the substation is a tap changer on the transformer. And we want to keep the voltage on the secondary rate of the transformer constant. The low voltage network that feeds the customers, you want to keep that constant no matter how much the primary voltage fluctuates. This tap changer on this feeder was operating 5, 6, 7 times per day. And then as all these homeowners added rooftop solar panels, the volatility increased, right? And now this tap changer is operating 90 to 100 times per day. Tremendous more increased stress. And the lifetime of this mechanical means of control is a lot less. So, you know, so I'll go back to here. So in Power Electronics magazine, I wrote this article, and I worked with San Diego Gas and Electric to have voltage waveforms from this feeder in the article. You should see the spikes and the oscillations of the voltage on this feeder. And the premise of the article was mechanical means of control with a future grid with high penetration of renewables just doesn't make sense because of the volatility. Mechanical means of control will just wear out too quickly. So let's look at new applications of power electronics. And from a university point of view, I still don't see the power electronics researchers working as closely as they should with power system analysis researchers. You know, my experience is power electronics is like an IEEE, the PELS, the Power Electronics Society, is their own society. Power Energy Society is their own society. And we never really did too much together. We did more with the Industry Applications Society, more of a sister society than PELS, okay? And then universities, you know, with the future grid, there's so much need for, here I just have 3 new applications of power electronics, but this is just the tip of the iceberg. The second one is low voltage network dynamic grid edge controllers. And that's what I'm showing here, where as you put more and more renewables like residential rooftops, the volatility on the low voltage network is huge. Look at the waveforms in my article. And what this is a power electronics device that we install on the low voltage network. Duke has a number of these installed. So they're all over the U.S., they're in Mexico, and they're primarily from a company called Verentech. Okay, and Verentech is in the Bay Area, California, but the co-founder is Dr. Deepak Dhawan from Georgia Tech, power electronics researcher, who was the president of the IEEE Power Electronics Society just after, around the time Al and I were presidents of Power and Energy. So what this does is a low voltage network dynamic grid edge controller that looks at voltage and reactive power as a set point controller.
So is this like back-to-back inverters with a better control system?
think of it as hierarchical control network, where the inverters are here. Number of inverters. Next level up in the hierarchy are these. And
I'm
then,
trying to visualize how it works, John. Is so it's power electronics, so are you converting to DC and then converting back to AC, or what happens
it's
inside?
trying to smooth voltage
Okay.
to go upstream. So all the the oscillations of the voltage, rather than letting those go upstream on the 13.8 kV network and trying to manage those with cap banks, let's attack it at the low voltage network. So it's smoothing out the oscillations of the voltage. Yeah.
One of the iterations on the driving revision of 1547 is the ability of the inverter at the end of the distribution swing to swing from watts to bars. And then the next question is, what strategy do you put in that inverter so it responds to a change in voltage at its point of interconnection? That's one of the things called the initial standard said the DER shall not attempt to regulate the grid at its connection. Now it says that with the agreement of the EPS operator, you can provide bar support and/or regulatory services at your point of connection.
So before that amendment, right, was passed, we weren't allowed to use the inverter as a bar resource.
No, the standard never said you weren't allowed. It said you shall not actively regulate. And I say that because with synchronous generation, I have always run them at less than unity power factor, which gives you a constant VAR input at the point of connection. It always matched what the power factor of the facility was to what I was putting out of the generator.
But with respect to inverters, the interpretation was.
Yes.
So with the amendment now, and that's why I added this, the third one here, what Jim just said was with the amendment now, we have more flexibility and capability to look at the inverter. And the question is, what additional functionality would we want in the inverter? California is kind of taking the lead on that. And the second thing is, to do what we want to do, what external control capability do we need? Think of this as a node in a network, right? So if we're going to send external control signals, what is it that we would want the inverter to do? And again, this is all power electronics. So that's my point is, there's so many things with power electronics that our experts in power electronics should work more closely with power system folks. Right? There's so many needs. Okay, let's go on to. So if we summarize this, what are the impediments? What are the enablers? So when we look at distributed generation, lack of transmission could be an impediment. Okay? And last night we talked about an example is the policymakers are driven to set policy, and typically not required, right, to do an operational analysis of the impact of the policy, or even if the policy is feasible. Right? An example we gave was in California. Policymakers said that by 2020, the 3 investor-owned utilities in California, 33% of their generation mix must be renewable by 2020. That was a substantial increase of renewables that had to be added to the grid in California. So after the fact, with an analysis that was done, it said we really need about 10 new transmission lines in the state to have the capacity to couple all this new renewable generation onto the grid. And getting one new transmission line in California passed is virtually impossible. The environmental folks, EMS, everything else. So, lack of transmission, lack of control area cooperation. And other thing with transmission is we have a lot of wind in the central part of the U.S., but there's not a lot of load there. So to capture that wind in the central part of the U.S., we need transmission to capture it and be able to send it then to where the load is. Okay? Lack of control area cooperation. One control area may have a tremendous amount of renewables, but they don't have a load that needs it. But another control area doesn't have the renewable, but a lot of load. So control areas cooperated with each other, have more spatial diversity of the resources. We could do a better job of optimization. Inflexibility due to market rules and contracts. Unobservable DGs, they're basically behind the fence. The utility doesn't know what's out there, doesn't have any information coming in, and so you don't know. Inflexible operation strategies during light load and high-risk periods. But enablers would be forecasting. You know, we've had some papers, some good papers recently from universities that had some good breakthroughs on better job of forecasting renewables. Okay. Thermal fleet, so some new equipment, new generation equipment with higher quick starts, deeper turn down, and faster ramps. More spatial diversity, one of the things we talked about. Renewable, distributed generation, and then grid-friendly renewables, which means that there's more information that we can get from those, and you know, they're easy to incorporate into the grid. So there's impediments and enablers. But I think one thing that we have to keep in mind is that when we look at large blocks of renewables, tremendous impact on the grid. We really need to study that and simulate it thoroughly before we make decisions. And so this is just some examples of some wind studies that the Energy Consulting Group of GE, who's based in Schenectady, New York. So this is a group, for the students that are here, this is a group that our expertise is modeling and analyzing the power system. Some of the world's top folks that write the key papers, with both IEEE and C-grade, that are the classic papers, you know, the industry follows. Okay? And you know, we were fortunate when I talked about 10 years ago, my son accepted an offer from GE. It was to join this group. There's not a better place to start. You know, you're surrounded by some of the best minds in the business, and you're working hand in hand with them on modeling the power system and analyzing the power system, and using tools like PSLF, maps. You know, these are tools that are used to model both from a electricity point of view, but also from an economic point of view. Tools that folks use. So these are some studies that are done, just a few of them, and it's very important, especially in Hawaii. We've done a lot of work in Hawaii, where anytime you have an islanded power system, it's very, very tricky, right? Because there's no tie lines to anybody else. An islanded system can't be supported by anybody else. So if there's a perturbation on the system, the frequency deviation on that grid is much greater than it would be in a 48 continental United States. They're all connected to each other. Okay. So in the IEEE PS, this was fun to do. We were asked by the Department of Energy to provide input on here for their Quadrennial Energy Review. So you can imagine you're a Department of Energy, you're going to put your budget together, and you say, what are the areas that we need to study in energy research? If I take out a crystal ball, but 10 years ahead, what's important in the energy field for the U.S.? I mean, what's the research we need to do, right? So you need, you know, you ask other organizations that have the expertise, help us with a crystal ball, you know, help us forecast. What are the key areas and what do we need to do? And that's what this was. So DOE asked the IEEE Power Energy Society, and they said, these are the key areas that we want your input on, okay? And so the IEEE PS reformed teams, and the second bullet here about microgrids and distributed generation, that was a team I led. I had about a team of 10 people, and we did work in that area. And so, final report was September of 2014, and so I'll just say that we did about 25 pages just on microgrids and distributed generation, and the other key areas did about 20 to 25 pages, and it's visionary. You know, what's the future hold for the U.S. in these different areas. And this information we posted on the IEEE website. This is public information, in addition to giving it to the DOE. Okay? So some of the things was microgrid and distributed resources are integral elements of the grid, so they can be operated islanded. But also, if they're connected to the grid, right? How do we look at that as the overall electric grid? The business case depends on benefits achieved not only for the utility, but the end-use customer. Okay? And the policy should support creation of value. So how can we make sure policy truly provides value to the end-use customer? Okay? And so here, look at capacity, reliability, power quality, energy efficiency and asset management, you know, reduced equipment utilization and losses, so generation is closer to the load, peak load shaving, in conjunction with market pricing, emissions reduction, trying to use renewables to a greater extent, and less of like the diesels, and cost savings because we're looking at a portfolio of resources and we're managing it locally, but we're also optimizing it on a system. So, utility grid and microgrids, synergistic. This policy supports value creation. The regulatory policy should reward costs. And costs and benefits should be a portion of multi-stakeholder microgrid business case. Again, I have an article on this in IEEE Electrification Magazine. And then new tools and standards, and IEEE 1547 is the most critical standard in this area. Okay, so let me finish. We're going to go to the IEEE student publication, November, December 2011. And again, if you'd like the full article, I can send it to you. Or you might be able to use the IEEE online search and go to IEEE Potentials and this issue. But so here I am in 1975. I worked in downtown San Francisco at Bechtel Corporation. And the style back then was a lot longer hair than I have today, and lamp and sideburns, right, and black glasses. So that was the style. That's why I look like that, right? But let me just go over quickly here before we finish. So I grew up in Chicago. I went to Purdue University, Midwesterner. But I'd never been further west in the state of Illinois my whole life, but I accepted a job in downtown San Francisco after I got my master's degree. So in 1974. So I say, go west, young man, my first job. So I was working, doing all the power system studies for what was the U.S.'s largest copper refinery that we were developing at Bechtel Corporation for the Mining and Metals Division. And I did all the power system studies. And I don't know if you've ever been in this situation. So I start work and I have a boss who, every time I was doing these studies, I'm explaining in detail to my boss and showing him my work. And then when the client came into town, my boss would be the one to meet with the client and explain all my work to the client and take all the credit for it. My boss never had me included in the meetings, never said anything. I just, it was like, I'm helping my boss get a lot of credit, and I'm not getting any myself, right? So I could have said, no, I'm not going to do this anymore. I'm going to do something else, try to find another position at the same company, or maybe leave the company. But I didn't. I enjoyed the work and I enjoyed the people I worked with in general. So I kept working, and I was really surprised on a Monday morning when I came into work, and his desk was empty, and all the books were gone. He wasn't on a project. And the chief electrical, who's in the white shirt back there, Chuck, came to me and he said, John, you know, I know you've been doing all this work. You haven't gotten credit for it. The project is going to be the same as it was. But now when the client comes into town, you'll present the work to the client. So it really worked out well, you know. It's fantastic. And it was a really good lesson for me. Don't let a disappointing work situation affect your attitude in work, because it will change. Nothing, right? Nothing in the world is forever. And don't have a knee-jerk reaction. Because if you do, there may be a situation that will improve and improve really well, which it did for me. Okay, that was a good lesson. Another one was we had a person sitting behind me who was on the phone all day making a lot of decisions for a project. And I kept thinking, if we ever lost this guy, you know, we'd be in big trouble. See you, Jim. Pleasure. Yeah. I said, we'd be in trouble. And all of a sudden, again, on a Monday morning, I come in and he's gone. He's not on the project anymore. And I thought, we're doomed, you know. And the project was very successful without this guy. So I said, wow, really no one is indispensable. And continue to do more than expected. So no one's indispensable. If you ever think that you're so important to whatever you're doing, that whatever it is, it'd be doomed without you, don't ever think that. Because that's not the case, okay? No one is indispensable. And so that you always focus on, I want to always do more than people expect of me, right? And I'm focused on value. How can I, every second of the day, how can I provide value to the person I'm talking to the group I'm talking to whatever the situation is. When I first started consulting work, people were paying $350 an hour for my time or whatever it was. And I'd lay at night in bed, having trouble going to sleep. I said, somebody's paying a lot of money for me tomorrow, right? The utility that I'm working with. I want to make sure they get their money's worth. I provide value every second, you know. And you just really focused on always provide value with whatever you do. Think about all the experiences you have, the knowledge you have, the contacts in the industry you have. How can you help a group of people? And then the short circuit studies I was doing. Remember when I was in graduate school, this was before HP and Texas Instruments introduced the first calculators. This was 1972 to 1973. We had no calculator, so I was using a slide rule all through graduate school, which meant, you couldn't be real precise, right, with the numbers, right, with a slide rule. So all of a sudden these calculators come out, and I started working, and I had HP's first programmable calculator, which is an HP 65. It had magnetic strips that were about this high and about this wide, and the little reader was just under the LED display, HP 65. So I wrote programs to do short circuit studies, parallel series reduction of complex branches, right, to reduce the network down to. And so I'm coming up with short circuit calculations with my new calculator, like 22,320.2 amps. Okay? And my boss says, and actually this is reversed, my boss says, John, what I want from you is accuracy without precision. And I really stuck with accuracy without precision. Be accurate, but don't overdo it. Right? Think about the significant digits of what you're doing. Because with calculators, the worst thing with slide rules, we couldn't do that. With calculators, you'd have all these digits after the decimal point. The other thing was I found that the business side of the technology is just as important as the technology itself. And it's just reinforced that with everything I've done in industry. So for me, instead of getting a PhD after my oral exams for my master's, I said, no, I was on a team that wrote the world's first three-phase unbalanced load flow in 1973. So today it's a standard application of a DMS. But we were the first group, 3 of us at Purdue, because our major professor wrote the very first book in 1968 called Computer Methods in Power System Analysis. It's the very first book on how to model the power system in a digital computer. Professor El Abiad. So he was my major professor. So we wrote the world's first 3-phase unbalanced load flow, got it to work in '73, and we couldn't do much more on a PhD thesis with that topic. But I said, no, 2 things. I want to start working and make some money. I've been a student all my life. The second thing, I wanted to learn the business side of the technology. So I went to University of California, Berkeley, and at night and got an MBA in finance. And that's key because you need to know the business side of the technology just as much as the technology itself. And then one thing that's very important in the United States, you never know what kind of job you're going to have. You always want to take the fundamentals of engineering exam, right? I took it while I was at Purdue at the university. You pass that, then get the work experience that you need, and then get your PE license, and your professional engineer license. So I took the test in 1978 in California, and then got registered in Pennsylvania here in '82, in Georgia in '86. And I keep those 3 registrations current, okay? And at Bechtel, my very first job, they wouldn't give me a business card until I passed the PE exam. So that was the incentive for young professionals. Once you started work, you didn't get a business card. We had a 17-week review course to prepare for the PE exam, which I took, passed the PE, and then I was instructor in the review course. I taught 2 of the 17 classes for about 5 years. So this is very important because there are times when I use my PE, there have been times when I've used my 3 different registrations with work. Take all the information that you have, your experience, your knowledge, and help others. Be a mentor to others. Okay? And in addition, for the last 4 or 5 years, I've been reverse mentored by a young professional at GE. So a young guy, University of Georgia, IT and systems graduate, joined GE's 2-year IT leadership program, 2-year rotational program, and he's been reverse mentoring me for about 4 years. Okay? And Computer World Magazine wrote an article on our reverse mentoring program. And has my reverse mentor Chris, has Chris's picture in it, and the value he's received from this reverse mentoring program. So mentoring is good, but also reverse mentoring. So he's helped me a lot with technology, the software applications at GE that helped me in my work that I wasn't aware of. And I've helped him with learning about the industry. And then lastly, I talked about this in the beginning, get involved in outside activities. You could, like at the university, you could do your classes and your homework and be okay, but at the university, look for outside opportunities like IEEE, right, to get involved with the chapter. When you start working, you can go to work every day, do the work, and be totally internally focused, just within your job. But you can be more valuable, both to yourself and to your company and to the industry, if you get involved in IEEE, the local chapter. Get involved in IEEE, like Al and I, with more of a national or international level. Write papers, teach courses, lead standards group. This is all volunteer stuff. All you got to do is volunteer and do it. Leadership opportunities, papers, take advantage of these and increase your network of contacts. Okay? Get involved in outside activities, giving talks, teaching courses, developing industry standards. You need to have a good balance between external focus and internal focus. Don't just be totally internally focused. Okay? Because you want to differentiate yourself against your peers, right? And everyone is going to go to work every day. Everyone's going to do the work with their business, but not everyone is going to get involved in outside activities. So there's 3 value propositions there that are all 3 important. In fact, we did a brochure for IEEE PS called What's in it for me? When you join PS, what's in it for you? What's the benefits? There's one level of benefits for you as an individual. There's one level of benefits for your company that you work for. And the third level of benefits is what you provide to the industry. Personal, company, and industry. And those are all three very important. Okay, so think about that. Think about outside activities. Think about getting involved with things. Volunteering for all kinds of opportunities. And you'll get more out of it. You'll be better off. And, you can bring more value then to your company and to the industry. So that's it. That's what I wanted to end with. So thanks. I don't know if we have time, we could have a few questions.
To me, it's up to the group here.
Okay.
Just before we take questions, for anybody that straggled in late, please make sure you sign the roster over there on the table on the way out. And if you want professional development hours, the instructions on there how to do it. John and I are captives here until my wife picks up John's wife at the airport and gets back here. So we're at your disposal until at least that time.
Yeah. Was this helpful? Especially the last part? Yeah.
Oh, I know there's such a focus on wind and solar. What about fuel cells? Do you have any thoughts on fuel cells and impacts and expansions in the future of fuel cell technology? And
We
how
showed
they impact the industry?
at Bella Coola, they had a hydrogen and fuel cell. So they had that there. But in the IEEE in fact, Cypher, Rahman led this. We did, at Washington, D.C., we did a hydrogen workshop, focused on fuel cells. And we had a pretty good crowd. But the consensus was that it's niche, but in terms of having a business case and feasibility in terms of widespread use and acceptance, it just wasn't there. It wasn't there. So we tried to kickstart it, have an industry experts together to look at technology, business cases, needs, and we never did anything as a follow-up to that because there wasn't the interest.
So at that one microgrid location, it's a small, a very tiny percentage of the output?
Exactly. Yeah. We tried. There were not a lot, but a core group of folks that really wanted to push it. So we did this. PDS sponsored it, but it didn't go any further.
John, it's an interesting thought because it was 10 years ago, it was seen as just an up-and-coming thing. It was going to be one of the great solutions to electric shortages and everything else. And
Right.
it just hasn't happened. Any insights as to why? What was the Achilles heel?
Well, it was
Go ahead.
cost. I mean, the business case, the
Yeah.
cost. I think the feasibility with the hydrogen and managing the hydrogen, and, maybe efficiencies, looking at all that. You're right. The question is, it was a while ago. We haven't done anything since. So the question is, have things changed? 10 years ago, the cost of a PV panel was a lot higher.
Yeah.
It's come down so much, PV's taken off.
I know there's been some fuel cell powered buses before. I've seen those news articles when those things happen, but it's not like it was such a wonderful improvement that all the other buses get converted to fuel cells.
Exactly.
Yeah, where was the hydrogen from? Where did they get the hydrogen?
Well, this was just in general, so I don't know specifically.
I meant at that particular site. That was,
Oh, here?
yeah.
I don't know. It's in British Columbia, like a third of the way, half the way up from the United States. It's rural, not connected. It's not near an electric grid. I'll tell you, you could Google Bella Coola. BELLICOOLA, Bella Coola, British Columbia. And probably find some reports and papers that were done on the project. That would have those details.
Because, I mean, Air Products is really pushing hydrogen. They have hydrogen vehicles that run around, but they're cracking petroleum, so.
Yeah.
I would just offer on that, we have some of the fuel cells that we've seen in our footprint are powered on natural gas. And so you've got a resource that's generating electricity that's combined heat and power, so it may offer very good efficiency, but you get into a question of it's not a renewable, so we're back to policy. And if it's not a renewable, then you could use it as a demand reduction behind the meter, but unless it can be represented as a qualifying facility as defined by FERC, you might not have a good way to export energy from that. So I've got a commercial customer right now with 6 locations that's going to put 6 installations in through PJM as a PJM export, and each of these fuel cells is 220 kilowatts. To me, that sounds like a lot of paperwork for a small block of generation.
I don't think there was one reason. I think there were a number of different concerns. It just didn't pan out in the business case. So the question is, we haven't, at PS, we haven't revisited like having an industry event in quite a while. Yeah.
How much do you think there will be micro PMUs or things like synchrophasers on the distribution level, and what kind of uses do you think there could be there?
So the question is, we there's a lot of work we can do that's with respect to PMUs, phasor measurement units, and synchrophasers. So we have this data, very different from SCADA data. SCADA data is every 2 seconds or 4 seconds. PMUs, many samples per second, right? But how do we make use of that? Okay, and one would be in a state estimator, which is typically an application that runs on an EMS for generation and transmission, right? But when you have the granularity of information coming in with many samples per second, you can look at transient stability, things that are shorter time frame, right? And have a better idea of what's happening to the grid. What we're finding now, a couple reasons, is we're using synchrophasers more on distribution. Reason is that we used to be that to get PMU capability, you had to buy a separate box. Now it's pretty much incorporated into every relay. So when you buy a relay, you have PMU capability, including distribution relays. Right. Second thing is there's an effort here. I showed distributing the intelligence from the control center to the substation. So what we're doing now is we're putting more applications at the substation level. And then at the substation level, instead of just SCADA input to the applications, we're putting SCADA and synchrophaser input. So we did a project like 2 years ago with PG&E in San Francisco, and it was their vision, substation vision of the future, and where we ran a state estimator in a distribution substation. Yeah. And the input to the state estimator is both synchrophaser data and SCADA data. And it's a full IEEE 61850 implementation. So a lot of new things there, and you're going to see more of that. The thing with, you're going to see. So we have the synchrophaser capability because it's part of the relays now. We don't have to pay extra for it. And the real question is, how can we make use of that information?
Do you anticipate using it in outage detection and in distribution networks?
Eventually, but we haven't even gotten to that point yet. Think about with distribution. When you had to put a DMS in, you need information coming from the field, right? You have all these high-powered applications, but you can only optimize what you know is happening. And of the 52,000 distribution substations in the U.S., only 2/3 today have any kind of automation installed. So when we add a DMS, we have to say, we want information coming back from our substations. And even less feeders have information on the feeders. So we call it intelligent line monitoring. So when we offer a DMS to a utility, we offer some amount of intelligent line monitoring so that the applications can have something to optimize and provide value. So we're just doing that today. So eventually we'll get to the point of synchrophasers, but it's like Maslow's hierarchy of needs. At the beginning, you have survival, food, clothing, and shelter before you think about anything else.
Yeah.
And so there's really foundational basic things with distribution before we get
Yeah, how much do you see the adaptation of 61850 over
there. It's been very slow in North America, and the reason is, in Europe, think about the European approach to substations is more of a turnkey approach. So if you're a European vendor, you get a contract to build an automated substation, and all the automation equipment is your own. It's very common in Europe and with European suppliers. So it's much easier to use 61850 because I have full control of the substation. In North America, it's not that way. Utility will say, well, I'm standardized on Bush, Schweitzer, and G relays. I've got a Beckwith load tap changer control. I've got a Bitronics meter. And so the ability to do 61850 depends, have all those vendors implemented it. Is it interoperable, right? And you become more of the integrator. So I can say, though, in the last couple of years, I've been on the advisory committee for Distributech since 1996, chairing the substation automation track. So I review all the abstracts that come in every year. And I chair at least one session every year. I've seen more and more sessions now with U.S. utilities, U.S. and Canadian utilities, with their experiences implementing 61850 in substations. So I see it happening, and it's growing. So eventually, what's going to happen is I see 61850 for certain substations will replace DNP. And those are more critical substations where you need peer-to-peer communication. You can afford Ethernet networks, you know. Smaller, like distribution substations, 61850 would be overkill. And so you stay with DNP. But as we get more experience with 61850, I see 61850 being used as the protocol from the substation up to the control center.
Yeah, I was going to ask about that because you only showed DNP out.
I really think that'll happen. But we have to get more experience and be more familiar with the substation level. Then it'll be up.
And how about sub-to-sub?
Sub-to-sub, to me, 61850 is ideal for that.
Because you do relay coordination.
You do it's designed for peer-to-peer communication. And you know, as we distribute the intelligence, right? My goal would be, I want to do as much as I can downstream and report after the fact what I did upstream. Well, if I don't have substation-to-substation communications, I can only do the substation and the feeders from that substation. And if I need to see 2 or 3 substations, I have to go upstream. But if I have peer-to-peer communications, I now know at the lowest level what's happening in my neighboring substations. I have more of an ability to make decisions down below and take more of the burden off of the master. So to me, I see more and more substation-to-substation communications. Makes a lot of sense. Good question.
Yeah, I was wondering, is there a limit of how big a smart grid can be?
To how?
Is there a limit of how big a smart grid can be? Like, can you connect countries with it? Like, just, for example, 3 countries with a smart grid. Is there benefit? Like, is it better to connect 3 countries or just to be like isolated smart grid?
Now, one of the things we talked about was, the more we can manage larger regions of the grid, and the more optimization is available, and truly the more benefits are available. Just think of distributed generation. Right? So but this part of the country, let's say, or this part of the European Union has a lot of wind, right? But the loads are light. We don't need the wind. But over here, we have a load, but we don't have the renewable. So if we can look at the spatial diversity, if we can look at a larger region, we can optimize it to a greater extent. Take more advantage of the resources we have, satisfying the load that we have, and also with respect to stability. When disturbance occurs, we have more resources available, right, to isolate and also help keep the grid stable. So to me, regional control, regional optimization is where we're headed. There's a greater goal to look at the regions, and what I said is coordinating across regions. So like PJM is an independent system operator, right? Same like Cal ISO, like Midwest ISO, like New York ISO, like New England ISO. But if those actually work together, right? That's a larger area that they're looking at. And by working together, there's more benefits available. No question about it.
Is it more of policy difficulties in having larger smart grids, or more of technological difficulties?
Truthfully, in that particular case, it's not technology, but it's really policy. And each of those ISOs are very different from each other in the way they operate, the types of market rules that they have. And so it'd be bringing together different organizations, different ways of doing things to work together.
So it's going to be a lot difficult to have different countries to work together and then different companies.
Yeah.
Okay.
Yeah. There needs to be something overarching, like maybe the European Union says countries in Europe. There's ENSO-E, for instance, in Europe. There's all the transmission operators in all of Europe. So ENSO-E is bringing together all the transmission of all the European countries to work as one. Grid codes, technology, policy, procedures. So there are organizations that are doing that. Like in the U.S. for generation and transmission, we have FERC and NERC. What's complicated in the U.S. is for distribution and the end-use customer, we have 51 different jurisdictions. 50 states plus the District of Columbia. Each of those has their own public service commissions that do have the rules for distribution and the end-use customer. So it'd be easier if there was a national way, right? There's 51. So like I said last night, if you're the CEO of American Electric Power, as an example, your utility, you operate in 11 different states. So for distribution, you can't have one smart grid strategy because the policies in a lot of states are very different. So what AEP has done, in certain states they have smart metering projects which are beneficial based on the policy here, but in other states they have more integrated whole bar control and no smart metering because of the different policies in the different states.
Okay.
If you guys are interested, we, in the Gridwise Alliance, which is a Washington, D.C. based organization, I'm on the board and I chair the technical committee. Every couple of years, we take all 51 jurisdictions and we rank them based on how supportive is their policy for smart grid investment. It's called the Grid Modernization Index. If you Google that, GMI. And we're gathering information now for the next edition of that. But you can see what are the top 10 states that really promote and support investment in smart grid, and what are the bottom 10 states. Because at GE, what we do is we look at two things. We look at the utility. We look at the utility and how much GE equipment do they have and what kind of relationships do we have with them. But depending on how, we say how much time should we spend with that utility and selling new things. We say, what state is that utility operating, or states? And how supportive are those states with respect to policy, right? Because you could spend a lot of time with a utility that's in a state that's 46, 47, 48. The utility may want to do things, but the business case is going to be tougher, right, to get across because the policy, the regulatory policy in that state isn't as supportive as other states. So what happens is the business case is going to have to really stand on its own without a policy component. Which is tougher to do. Not impossible, but tougher to do.
One more,
Sure.
I'm just curious, just adding on to that, are there any places in the country or the world that are so good at promoting renewable resources and distributed generation that it's creating technical challenges that are almost like, at the limit right now and are almost like beyond the technology because they're so good at it, or so promoting it so widely?
Yeah, no, that's good. I have a set of slides just on policy, and it shows why when I say policy is the most important driver for investment. And I show examples of that in a lot of the countries in Europe. Beginning in 1990, 1991, 1992, a very effective policy was passed. And the important thing was national policy. So I said, for distribution, we have 51 different jurisdictions, so it's fragmented. Well, if you have a national policy, it's going to mobilize the country to invest, right, on a countrywide basis. So places like Germany, Denmark, Spain, tremendous amount of renewables, particularly wind, solar. And it's because of policy that goes back to the early 90s. It was very effective. But, in Germany, there's so much renewable, there's so much intermittency that, how do you bridge that intermittency when you have such a high penetration? And I understand that, you just can't get enough storage, to back it up, and they're actually building new power plants like the backup to high penetration of renewables, because you have constant load. And if you've got 60, 70, 80% renewables, all of a sudden the wind goes away. The load still has to be used. So yeah, there's real problems in these countries. They're the pioneers. And the worst thing you do, and I understand this was happening in Germany, was building a coal-fired plant, right, to help back up large-scale renewables. So the renewables help the environment, but you have so much and so much intermittency. Your best solution is a coal-fired plant.
As I say, we'll take one more question and then we probably need to pack up.
Okay.
But while we're packing up,
just
somebody
gonna
can come up
say
and ask John.
If John comes back, would there be information on vehicle electrification and how that's affecting, or how smart grid is helping with that?
Yeah, we, a couple things with that. One question was, we have a lot of generation resources in the U.S. that we turn down overnight. And the DOE did a study that said, how many electric vehicles could we charge overnight if we didn't build any new power plants? And we could charge over 10 million electric vehicles in the U.S. with just the power plants we have today. So to me, the emphasis is on, intelligence in the infrastructure. How do we do that? The other challenge is the customers of electric vehicles aren't equally spaced around the distribution system. So you get more affluent subdivisions that have high concentration, which might be all on the same distribution transformer, right? And then other subdivisions where the lower priced homes where people can't afford to use, right? So to me, the challenge is, as a planner, to anticipate which pockets of your customers have a higher probability of using EVs in a large percentage, and how's your grid, your feeders, your transformers, and your grids, your substations, going to handle that. And then when you come home from work at 5 or 6, you don't want to plug in your EV without any intelligence there. That's your evening peak. And we don't want to make that peak worse by all these EVs being charged at peak time. So how can we put intelligence in the infrastructure to delay that until about night or midnight? There's different charging algorithms that are being looked at. And that's far from, PG&M has done tests on vehicle to grid, and Google did with PG&E. See, you get a bunch of cars, batteries are charged, and you take the energy from the batteries and feed the grid. So you go vehicle to grid. To me, that's down the road.
Ideally, your electric car would be charging while your solar panel's at its max, but
Right.
it's usually 100% opposite of it.
We did, you can find this on IEEE TV, we did an 8-minute smart grid video. And we had an energy conference in Atlanta. I'm speaking in the video, so is Deepak Damand. But we're up on the roof of a guy's house in Santa Monica, California, and he's explaining to the reporter. He says, yeah, he says, I put these PV panels on my roof. He said, and the business case pencils out real well with Southern Cal Edison. He says, I can buy power at 10 cents a kilowatt hour, but any extra power I generate from my home, I can sell it back to Southern Cal Edison at 40 cents a kilowatt hour. And that was the policy at that point from the CPUC, the California Public Utility Commission in California. I said, oh my God, you know. And so he says, yeah, I got rid of my internal combustion car. I have a pure EV now. And I charge the batteries from my own generation on my roof. So that's additional savings for him. I said, gee, you know, 10 cents to buy and 40 cents.
Gas strips are a wonderful thing. Oh, I'm sorry, where does the money for those gas come from?
You, every other customer.
Very,
No, that's where the money comes from.
yeah, us, yeah.
All right, great, John, thanks very much.
All right.
Appreciate it. If everybody else has any burning questions, feel free to come up while John's packing up. I'm sure we can answer them. But I'm glad I saw the guys out there taking back all the brownies and coffee, so I'm glad I stole one for John before the meeting.
We can eat the rest of it.